Hello AP Physics students. Welcome back. It's Mr. Kennedy again. Hope everybody's doing great. This is our last video to review. Actually, it's our last video total. This is our last talk about mechanics. We're going to talk about rotation today. And then that's it. Then it's just time to get ready for the AP test. And again, practice, practice, practice. That's the way things are going to go really well for you. So rotation. Let's actually take a look at the whole unit of rotation. There's a lot in there. And break it down to some of the bigger concepts that came up. But in Unit 5, rotation, there's really four parts. The four parts are motion, what we call dynamics, then we have energy, and momentum. So those are the four big parts in this unit. And they mirror the first four units of AP Physics as well. So the fifth unit, if you know rotation, you're going to probably know everything else that comes after it, or that comes before it actually. So let's take a look at motion. So the first part was describing motion that moved in some kind of circular pattern. So motion, where normally we would describe things with position, velocity, and acceleration, and we use S for position because it's really arc length here. Now we describe things with theta, omega, and alpha. This is position, that's angular position. This is velocity, that's angular velocity. This is acceleration, that's angular acceleration. Now if things move in such a way that there is a constant angular velocity, just like there'd be a constant regular velocity, if that's the case, then theta is omega times time, because this is going to be something that moves at constant velocity. If we see that something moves at constant acceleration, constant angular acceleration, then we would have a mirror of all of the equations that we had before with just linear motion. We would see that with angular motion. Omega equals omega naught plus alpha t. Theta equals omega plus omega naught divided by 2 times t. Theta equals omega naught t plus 1/2 alpha t squared. And omega squared equals omega naught squared plus 2 alpha theta. All of those are mirrored from the equations we would have for normal kinematics with constant acceleration. The same thing happens for these equations for angular acceleration. And these are derivatives. The derivative of position is velocity. The derivative of velocity is acceleration. The same thing is true here. The derivative of angular position is angular velocity. The derivative of angular velocity is angular acceleration. So there is a direct mirror of the things we saw before. And again, this, remember, is constant velocity, constant angular velocity. These right here are constant angular acceleration. So be careful with that. Now, how are these linked? Well, these are linked by the radius. If you'd like to find out something on an angular quantity and go to the linear quantity, multiply by the radius. So the base for this is S equals R theta. Then if I move down the row, V equals R omega, and then A equals R alpha. So these quantities are not dependent on the radius. These ones are. The further out you are on a circle, we've got a circle right here. If I'm here and I go around a circle, and if I'm here and I move around a circle, the bigger radius had to move in a bigger path, so it had to also be moving faster compared to everything else. So the first part of this unit is all about motion. The second part, which I'll call dynamics, is really about the causes of motion. Now, in linear terms, forces cause changes in motion. But in angular terms, you need something else. You need something called a torque. And a torque is going to cause something to change its rotation. So that is R cross F. But it's probably a little bit easier to just deal with RF sine of theta. That you have to have some radial arm times the force times the angle in between them. Now, Just like force causes something to, an unbalanced force causes something to accelerate, an unbalanced torque also causes something to accelerate, but accelerate linearly. And where we have F equals ma for linear things, we have torque equals I alpha for angular things. Now keep in mind, you might remember from when we did this, you are oftentimes going to have to set up a linear side and an angular side to solve problems. That there are going to be, very often if something is going to move and rotate, you'll have to do this. Like for instance, a ball rolling down a ramp would be a good example if you're trying to find the acceleration. Now this piece right here, this is the moment of inertia. Moment of inertia is the rotational version of mass. It's how difficult it is to rotate something. And it's given by the sum of all mr squared. That's for a point mass. However, I would know all of the basic ones. I would have them definitely memorized. That's a hoop, a disc, a sphere, rod, pivot in the middle, rod, pivot in the end. And remember, you can program all the stuff in your calculator anyway, plus it's an open note test. So I would just have them known just so you would do that as quickly as possible because it is under time. Now, one other thing that comes up with moment of inertia is the moment of inertia at any point is the moment of inertia at the center of mass plus mh squared, where h is how far you move it over. So if you move something from its center of mass, you're going to have a bigger moment of inertia. It's going to be harder to turn. So setting these problems up is definitely critical. Again, one of the things that people forget is this r when they put it in to torque. So it's very often you'll be setting torque equals rf sine of theta equal to something with I alpha as well. So that's why some of these problems seem so complicated, because you're doing so many new things at once. Torque here, I alpha here, the moment of inertia here, what the shape happens to be. So practice and practice and practice with dynamics. Now, the next phase of this dealt with energy. And when we reviewed energy, we said that conservation of energy is still going to be one of the key things. And that's not any different. All we're really doing here is we're really introducing the fact that things that rotate are going to have this energy, 1/2 I omega squared, where I is the moment of inertia and omega is the angular velocity. This mirrors 1/2 mv squared that you have for your normal kinetic energy, which is 1/2 mv squared. I is the rotational version of mass, v is omega is the rotational version of v. So it works out really well that you're not really learning something completely new. But with energy conserved, you're just trying to put the energies here in the beginning equal to the energies you have at the end. It's possible we could change the energy. That would be work done, so there would have to be some kind of change in energy. Like if I sped up, there had to be some kind of energy that I added to the system. And I could subtract beginning from end to find out how much work I did. But if you do have something like a ball rolling down a hill or something, you want to find out how fast it's moving, it will have both types of energy. And you'll have to make sure to put them both in. Now, one thing that they often will do is they'll often make it so that the M's don't quite work out, don't quite cancel out. Just make sure you're putting in what's spinning and what's actually moving. This has to be moving linearly. This has to be spinning. So ask yourself what quantity actually spins and what quantity actually moves. But you're really just adding that to the conservation of energy. And the last one was momentum. But this time it's different. This time it's angular momentum. And it mirrors what you had from momentum before. Angular momentum is I times omega, the rotational version of mass, times the rotational version of velocity, where regular momentum is just mass times velocity. So there's a nice parallel here. Now, with this, what you're really doing, the number one concept you have is that you have a conservation of angular momentum. And the typical example I like to use is the figure skater, that the figure skater goes into her turn with a really big moment of inertia and a small angular velocity. And then as she pulls her arms in and legs in, she has a smaller moment of inertia because the mass is closer to her now, and she spins faster. So that's the one way I like to think about, just conservation of angular momentum as a whole, but there could be many things that are actually oscillate or rotating in here. So you want whatever's spinning here, whatever's spinning there. Maybe you have two things that are spinning and then they become one later. Whatever it happens to be, you have to analyze that situation so that the angular momentum turns out to be the same before and afterwards. Now in regular momentum, we saw that the change in momentum per time, that was a force. And you could just say derivative too. The derivative of momentum per time is a force. But there's an exact parallel if you're going to change the angular momentum. The change in angular momentum over time is a torque. And that's the derivative of momentum with respect to time. So whenever you have the beginning equal to the end, you have conservation, but if something has been added, there must have been some kind of angular impulse that was actually added to that as well. So really rotation, if you know the first 4 units well, then it helps with rotation. And if you know rotation, it helps the other 4 units that you did before this. So it is really possible to see some of these things combine as well. You could see problems where you have things that are rotating and maybe colliding or doing all kinds of other things. Just think back to the concepts and it will make the most sense. All right, so it's time to practice. We're done reviewing. I'll have tons of extra practice for you to do as you're doing it. Any questions you have, please feel free to email me. But hopefully this helped you put some things back in perspective and wake your memories up a little bit. But now it's just a time to practice. There's a very good chance that one of the problems that you're working on right now could be one that is on this year's AP test. So the more you practice, the luckier you get. All right, everybody, I hope to hear from you.